Yes, we can begin now. So today's next talk is by Arushi Bodas from University Chicago and Fermilab, and she's going to talk about seeing particles beyond the inflationary Hubble scale. So maybe I'll send you a reminder when 5 minutes are left.
All right, thank you so much. Thank you so much for the kind invitation. So today I want to tell you a little bit about cosmological collider physics, aka a way to see particles at the inflationary Hubble scale. And this talk is based on these two papers. So this was done a couple of years ago with Shobhik Kumar and my advisor, Raman Sundram. And this paper we put out a couple of weeks ago with Edward Broadberry and Raman, and it is kind of a follow-up. So hopefully together they paint a nice complete picture. Okay. So I'm guessing no one in the audience needs any real reason or motivation to believe why cosmology is important, but let me just say a few words. So cosmology allows us to look further back in time when our universe was more denser and hotter, and hence it's kind of a natural laboratory. It's kind of a given to us already, and so it's a very natural place to look for interesting high energy physics. So the question is, how far back can we look with this approach? And there's a very unique observable, which is the density inhomogeneities, which can allow us to look all the way back to the beginning of your universe, which is the epoch of inflation. Now, of course, you must have all seen these beautiful pictures of temperature fluctuations in the CMB. We know the beautiful cosmic web. And although a lot of these things are an effect of the nonlinear effects of gravity, if you kind of remove them, we go to the seeds of these inhomogeneities, which are the primordial inhomogeneities or primordial fluctuations, and they can be related directly to the quantum fluctuations that are generated during inflation and stretched out by the exponential expansion to become macroscopic fluctuations. As we don't know exactly the scale of inflation, but we know that it can be as high as 10 to the power 13 GeV, which means that these density inhomogeneities are giving us a way to look all the way back to these really high energies, a possible way to look at really, really high energies. So this is a very interesting observable, and let's see what we can do with it. So to kind of elaborate on this connection between quantum fluctuations and density inhomogeneities that we observe today, let us look at how these are generated at the end of inflation. So let us look at some vanilla model of inflation where the inflation is driven by a single scalar field, which we'll call the inflaton phi. And very standard picture is that this field has a very flat potential, and there's like a valley at the end. So when the field has this vacuum expectation value somewhere here, it kind of slowly rolls along this plateau-like part of the potential. And if this field is dominating the energy density, this just acts like a cosmological constant and drives a de Sitter phase or inflation. And as it rolls down, it will eventually reach this end part where it will roll into the valley, ending inflation. And its oscillations can convert the energy that the inflaton had into the kind of lighter particles that it couples to and reheat the primordial plasma. And so this is the basic picture. But of course, on top of this classical background, there must be quantum fluctuations. This is a quantum field. And so in different patches of the universe, the field value can be slightly ahead of its vacuum expectation value or slightly behind. And based on that, the inflation can end a little early or a little late in different patches of the universe, leading to a small overdensity or small underdensity in these parts. And this kind of time delay relates the fluctuations, this kind of time delay that controls when the reheating happens, And when the energy density starts diluting like radiation, it converts the fluctuations of the phi to the fluctuations in the temperature of this primordial plasma. So there is like a very nice simple relation between the fractional fluctuations that you observe in the temperature or density that can be related to this time delay between the end of inflation between different patches, which can be related to the fluctuations of this field phi. And in the gauge invariant, observable is actually the ratio and this quantity. So this is kind of the link between the two. And we know that the anisotropies that we observe today are at the level of 10 to the minus 5 that we observe in the CMB. And this also kind of gives us additional information that in a kind of single field kind of vanilla model, the kinetic energy of this rolling field is much, much bigger than Hubble. It's smaller than the potential energy, but it's still bigger than Hubble. And this point will come again later in the talk. So just keep this kind of thing in mind, that the kinetic energy is much bigger than the Hubble of inflation. Okay, so as I just said, just to reiterate, the density fluctuations that we observe today, the statistics of these fluctuations can be directly related to the statistics of the quantum fluctuations of the inflaton at the end of inflation. And currently we know that we have only observed see that these fluctuations are Gaussian in nature, so which means that the only non-trivial correlations are in the 2-point function. And this can be modeled very nicely with the inflaton being just a free scalar field. But future observations of large scale structure or 21 centimeter when we observe it will be able to have more data and can probe even small non-trivial higher point correlation functions. And kind of the simplest is the 3-point correlation functions between these density perturbations. And if such non-trivial higher point correlation functions are observed, they can directly tell us that the inflaton was not free field, it had interactions. It can give us a lot of information. The kind of correlations that we observe can give us a lot of information about either the potential of the inflaton, higher point, just various interactions of the inflaton with itself, as well as with other fields that are hanging out at that inflationary scale. And this second part is of interest to us in this talk, where we want to, using these higher point correlation functions, we would like to probe heavier fields during inflation that may be talking to the inflaton. So yes, our goal is to use higher point correlation functions to detect particles at the inflationary Hubble scale, which can be as big as 10 to the 13 GeV. So it's a very, very different and complementary way to find high energy physics than the terrestrial colliders that we usually know of. So from now on, our observables will always be these density correlations, but because of this connection, I will only focus on the correlations of the inflaton and evaluating them. So we'll just kind of focus on this part of the diagram from now on. Okay, so what is the signature of the heavy particles that may be talking to the inflaton during inflation? So this is basically the idea of cosmological collider, which was initially proposed by Chen, Wang, Naomi Yamaguchi, and Yokoyama, and later expanded on by Nima, Maldicena, and many others. Actually, this is the paper where the name was devised, cosmological collider, and we'll see why the name makes sense. So here we have just the diagram of inflation. We're studying 3-point correlation function of the inflaton, which is represented in blue. And just consider some heavy particle, let's call it sigma. So the signature appears in not real space, but in the momentum, in the Fourier space, which has 3 momenta, K1, K2, K3. During inflation, the spatial translation is still a good symmetry. So these momenta should add up to 0. So you can think of them as a triangle. Now, the interesting signature of this correlation appears when you consider specific shape of this triangle and the correlation in a specific limit, which is called the squeeze limit, where you consider that correlation when two of the momenta are much bigger. The hard, let's call them hard momenta, compared to the third one, which is the soft momentum. And in this limit, if the mass of this sigma field M is bigger than the inflationary Hubble scale, the correlation has this unique form where basically it depends on the ratio of the soft momenta to hard momenta to some imaginary power. And the imaginary power depends on the ratio of the mass of this heavy particle to Hubble. And what that means is that if I study, if I vary this angle, so if I vary this ratio of soft momenta to hard momenta, which is kind of shown in this plot here, if I change the correlation and change the triangle that I'm looking at and go to more and more squeeze triangle, this correlation actually oscillates because of this imaginary power. And the oscillation frequency is directly related to the mass of this heavy particle, which means that if we actually observe such kind of correlation, you would be able to detect, you actually first of all detect an actual heavy particle, and you can get its mass. Also, it turns out that there is a third, there's a second parameter in this triangle, which is the angle between these two momenta, which is theta. And for higher spins, there is also a unique dependence on this theta, which means that you can not only see the mass of this particle, you can also comment on its spin. And this is nothing but like directly seeing the particle. This is sort of like the resonance in usual colliders. So this is really the way to directly see heavy particles and detect them through non-Gaussianities, through higher point or 3-point correlation functions in these density perturbations. And because it's like happening on cosmological scales, hence it was called the cosmological collider. So everything is great, but then you notice that there is this other factor sitting in front, which is exponentially small when the mass of this heavy field is bigger than Hubble. And this is kind of a painful thorn in this program, where you have this amazing signature where you can detect particles through non-Gaussianity, but the signal becomes quickly small and exponentially suppressed. So the goal of this talk would be what is the origin of this exponential suppression of these signatures? Is there a way to get around? Is this exponential suppression inevitable, or can we reduce it and hence increase the reach of the cosmological collider? And I'll show that there are some mechanisms termed chemical potential which can do it. And then I will first show our mechanism for the scalar fields, and then later generalize it to vector fields and show its application to potentially detecting gut models. Okay. So the first point is to understand where the exponential suppression is coming from. And for that, we need to understand where this oscillatory signature or non-analytic behavior in the correlation function is coming from. And it is very intimately tied to the cosmological particle production. And the idea is that if you have time-dependent space-time, it necessarily introduces explicit time dependence in the Hamiltonian. And if you have a time dependence in the Hamiltonian, you can have excitations even when you start with the ground state. And to see this, we can take this massive field in second quantization and look at its mode functions. So the equation of motion is just given for a simple scalar field is given by this equation. And right away, we see that the frequency term of the mode function, it has the usual momentum piece and the mass piece, but it changes with time. Here, eta is the conformal time. So as the as the conformal time changes, the frequency changes, and it therefore has a very explicit important time dependence. Now, this equation can be solved exactly, and the solutions are Henkel functions, but it is useful to see the early and late time limit of this function to understand this particle production that I was talking about. So if you take the early time limit of this function, then it has a very at early times, we know the momentum should be blue shifted and momentum must be more important. And as expected, it has a plane wave form with the energy which is just given by the momentum of the mode. And of course, we choose positive frequency solutions such that at very early times when the modes are highly subhorizon, they're effectively in Minkowski vacuum, and hence the vacuum is simply the positive frequency components. But if you take the late time limit of this mode function, you will expect that the momentum must have redshifted, the mass is now important. And as expected, there is the energy is just now the mass. You get the e to the IMT kind of usual oscillatory behavior. But you also notice that there is a small negative frequency component that has developed at late times. And so this is basically the idea that in the Heisenberg picture, if you start with some ground state at early time and you evolve it, it will not be the ground state or the lowest energy state at late times. And the state is basically, at late times, it looks like a superposition of the lowest energy state with, and on top of that, there will be amplitudes for 2-particle states, 4-particle states, etc., etc. And so this is the idea behind cosmological particle production. And this the amplitude for this 2-particle state will be important for the cosmological collider signature. So so in this way, when I think about kind of particles being produced because of this expanding background, I can think of this 3-point correlation diagram as the Hubble kind of producing 2 massive particles because of the time dependence in the background. And then these heavy particles with opposite momenta kind of propagate and then decay to the inflaton through their coupling to the inflaton. So the process just becomes a production and decay of these heavy particles now at one end into one soft mode of the inflaton, and on the other end, 2 hard modes of the inflaton. And so because it's just the decay process, what we need to know is when is this decay feasible? So now in the usual Minkowski space, we just have to ensure that the energy is conserved at every vertex. In inflation, because the energy is constantly, the momentum is constantly redshifting and the energy is actually changing, there is only a unique time when the energy of this massive particle will match the energy of the outgoing inflaton field. And that's when the decay or this diagram has maximum support. And those times are completely fixed by these momenta that we choose to observe our correlation function then. So here I'm showing that the time when this TS, when this decay into soft momenta is happening, is completely fixed by what the soft momentum is. And similarly, on the other end, the time when this decay into hard momenta happens is completely fixed by what the hard momentum is. And now, so the way this affects the correlation function is when we're looking at the 3-point correlation function. Now, notice that this is different from the amplitude square that we have to do for transition matrix. This is because it's a correlation function, the amplitude of this process will get registered, which means that the additional oscillations of e to the IMT that happen when the particle is propagating differently, these 2 particles are propagating differently, that phase difference will get recorded in the 3-point correlation function. And the phase difference should just be e to the IM, the time difference between these 2 decays. the T hard and T soft. And as I said, the times are completely fixed by what the momenta is. So if I convert this time difference into momentum, it becomes the ratio of the two momenta, K soft to K hard. And we recover the kind of oscillatory signature with which has the ratio of the momenta, and it has an imaginary component, which gives you the oscillations, characteristic oscillations in the cosmological collider. Okay, so in this way, the cosmological production is directly related to the oscillatory signature that is unique to cosmological collider and hence lets you detect particles. But it, of course, depends on this beta factor. If I go back, this was the factor that told us what is the amplitude for particle production in the first place. So this beta, it turns out is small, and you would, of course, expect it. It's not surprising because if you're trying to produce particles that are more massive, are heavier than the background expansion, which is Hubble, of course, for more massive particles, you would expect a smaller amplitude of production. But unfortunately, it's not a polynomial suppression; it's actually an exponential suppression. And this was the origin of this was the problem in the beginning. This was this exponential suppression. And a quick way to understand why we expect this amplitude to be exponentially small is one can think about it in terms of how much the adiabaticity is violated. I think a more intuitive heuristic is to think about the background kind of providing energy of order Hubble, or the energy of energy of order the Hawking temperature of the de Sitter space, which is just Hubble over 2 pi. And so if you want to produce anything which is more energetic than this Hawking temperature, then you would kind of expect some kind of Boltzmann-like factor in the amplitude. So from that, I would expect this beta square, which is the probability of having an excitation, to be just e to the minus delta E, which is just the mass of this particle, m over the Hawking temperature. But remember that in our case, we are not actually getting a full suppression of the probability, but the amplitude is what is getting registered in the 3-point function. So we pay the cost of the square root of this probability, and that this kind of heuristic actually exactly matches the beta factor that you get from the actual calculations. So what this is telling us is that, yeah, I can actually think about it as production from the background, but I should always kind of stick this exponential suppression in the amplitude while thinking about cosmological collider. And the problem here is, of course, the oscillatory signature kind of only appears when m is sufficiently larger than Hubble. But the exponential suppression kind of quickly kills it when you try to go beyond Hubble. And when the mass is smaller, the imaginary component actually becomes real at some point, and it becomes, instead of an oscillator signature, it kind of becomes a real power, which becomes harder to distinguish from other types of non-Gaussianity. So you kind of lose the kind of detecting particle aspect through this in those kind of non-Gaussianity. So your window of directly observing heavy particles with this mechanism kind of gets very limited around the inflationary Hubble scale. And so that is kind of the problem. And the question is, can we get around this? Is this inevitable, or are there mechanisms where you can kind of extend this window and hence kind of have more reach using through this mechanism? And of course, the answer kind of lies in the problem itself. So the problem is that the background expansion is only at Hubble, and it's not able to provide enough energy to make these heavy particles. So the solution must be, can we find another source, maybe which is bigger than the Hubble of inflation, to produce these heavier particles, and maybe that will get rid of some of these exponential suppression. So yes, that is basically what chemical potential does in usual thermodynamic systems. It kind of instead of temperature being the limiting factor, you can actually populate states all the way until up to chemical potential in a thermodynamic system. And hence, this mechanism was termed chemical potential. And so what can this source be? So if you remember in the beginning, we saw that the kinetic energy of the inflaton is smaller than its potential energy, but it's still much bigger than the Hubble scale. And so that can be a very good source. So if we can somehow use the kinetic energy of the inflaton to produce these particles, then we can probably do better than just Hubble. And this is indeed the way. So first, in the first case, I will show you how to realize this chemical potential for spin zero fields that we had worked out. But of course, people have also worked out realizations for spin half, spin one, and spin two fields. And if anyone's interested, there are all these references which are very good. I have a comprehensive kind of summary of how the chemical potential works for these higher spins. At the end, I will also show the generalization of the R spin zero mechanism to spin one, which is kind of different from what has been discussed in the literature before, but it's kind of connected and interesting in its own way. Okay, so let us first do a very simple case of a complex scalar field and see how the chemical potential can be incorporated. So in the usual case, thermodynamics, the way to incorporate chemical potential is just adding a number density operator to the Hamiltonian with the Lagrange multiplier. That's the chemical potential. Now, for a complex scalar field, there's a very natural current just given by this, and the corresponding charge, the conserved current, a conserved number is basically the number of particles and number of antiparticles. At the level of Lagrangian, doing this is simply kind of adding these additional terms with the time derivatives, which can be thought where the chemical potential can be thought of as kind of a constant zero component of some fake gauge field. And if I just expand this out, you'll see that I get the exact operator where chemical potential coupled to the J mu current. Now, typically, this is non-trivial in thermodynamic system because it's coupled to a thermal bath. But in our case, there's no actual thermal bath during inflation, and so our complex scalar is like an isolated system. So we all know that a constant zero component of a gauge field is trivial. It can be rotated away, and that's exactly what happens if you just have this kind of coupling. I can do a field rotation on this complex field sigma and get rid of these terms and go back to just the free field. And what is lacking is this connection to the thermal bath. Because in inflation, there is no actual external thermal bath, we have to kind of simulate it ourselves. And the simplest way to do that is add a small U1 breaking term, explicit U1 breaking term. So in addition to the U1 preserving terms, we will add the simplest kind of linear U1 symmetry breaking term in the form sigma plus sigma dagger. And now if I perform this rotation, the chemical potential will kind of disappear from these terms, but it will still stay in these terms that break the global U1 of sigma. And so the effect will be now non-trivial. And this is kind of what we want to do and kind of do it in inflation. So what we want to figure out is how do you get chemical potential? What kind of coupling to the inflaton do we need to kind of get this kind of coupling for the complex scalar field? And it turns out to be very simple to do. All we have to do is basically couple the current of complex field to the d mu phi term of the inflaton. And this is also nice because you typically want to couple anything, the inflaton, the additional couplings of the inflaton kind of should be derivative, so that it doesn't introduce any correction to the potential. And so you don't kind of mess around with the slow roll parameters. And so with this kind of derivative coupling to the inflaton, when I put inflaton to its wave, this the zero component, so phi, which is just the kind of kinetic energy over lambda, becomes the chemical potential small lambda. And I can follow the same steps as before, and where the d mu phi term is now appearing along with this time derivatives. And just like before, I can do a phase rotation of sigma to transfer the d mu phi term from these from the kinetic term onto the symmetry breaking terms here. So this kind of rotated basis is more useful. We found when doing calculations or kind of keeping track of what chemical potential is doing. So in the rotated basis, the Lagrangian of this complex field just has its usual terms, kinetic terms, mass terms, and the symmetry breaking term along with this additional phase, which is e to the minus I phi over lambda. Now I can break it down into the wave and the fluctuation of the inflaton. The wave part just turns into chemical potential times time, e to the I lambda t. And we have some fluctuations that will generate interactions between the complex scalar and inflaton. But the important point here is that now you in your interactions, we have this explicit time dependence with very high frequency, because lambda now is the chemical potential and can be higher than a Hubble scale. So we are kind of have introduced an explicit time dependence that is, first of all, different from Hubble and can be bigger than Hubble. Now, how big can it be? So to maintain perturbative control, what we need is that this parameter should be small, and that just tells us that this chemical potential lambda should be less than about 60 Hubble, which is still good. It's still bigger than Hubble. So we have bought ourselves a window from Hubble to 60 Hubble, and that's good. So let's see. So as I was saying, in the calculations now, whenever we have interactions, we also have this explicit time dependence coming from the chemical potential. And I can think of this as just, in my diagrams, I can think of it as injecting or removing energy of order lambda from each vertex, depending on if I'm looking at this piece or its complex conjugate. And so instead of like now being restricted to Hubble, we have this much more energetic source to produce particles, and hence we expect some of the Boltzmann suppression to go away. Just to give you a quick idea of how the calculations are done, so these kind of modified Feynman diagrams are computed in this something called as in formalism, where in the usual case, we have transition amplitude, so we have in state and out state. But here, because we're doing correlations at the end of inflation, we just have just the in state coming from the infinite past, and we just take correlations at the end. So we, as I said, for all the relevant modes at very early times, they should be in Minkowski vacuum. So you can start with the kind of what is known as a bunch-Davies state and evolve it with the interactions, and to get the state at the end of inflation and calculate correlations at that surface. And the I epsilon prescription just ensures that you project onto the interacting vacuum in the far past. And now in our diagrams, the leading contributions come at tree level. So we just expand it to leading order, and these are the important terms. And the calculations are a bit tricky because, as I said before, the mode functions for these heavy particles are not just plane waves like in usual case, but they have these Henkel function, or they're Bessel functions. So the these time integrals are kind of tricky, but it can be done. And so I will not go through the details, but what is important is at the end is the 3-point correlation function appropriately normalized by the 2-point function, and it's typically denoted by this thing called FNL, this parameter, which we can compare to the projections from the experimental side. So at the end of this calculation, this is what we would calculate and compare. So here, let me show you what the results for this FNL are. So the form of this 3-point correlation function of non-Gaussianity is given here. So if I maximize FNL, so if I consider the biggest coupling I can take between the inserton and the heavy field within perturbative control, within observational constraints. So I have taken the largest coupling and plotted the FNL values as a function of the mass of the heavy particle in Hubble units for various values of chemical potential, 10 Hubble, 20 Hubble, all the way to 60 Hubble. And we see that this FNL, or 3-point function, that we would have expected to drop exponentially is now kind of remaining kind of not really large all the way until you go to you hit chemical potential, and after which again there is a sharp suppression, because again, as expected, you don't have enough energy to produce particles which are more massive than chemical potential. But as expected, there's a larger window in which the non-Gaussianity is observable, is large, and we have kind of delayed the exponential suppression until chemical potential. To get a sense of, in terms of observations, what is the prospect for observing these kinds of FNL values, let me kind of give you quick projections of some of upcoming experiments. So of course, CMB, we already have observations of CMB, and we haven't seen non-Gaussianity, and it kind of places a bound at somewhere, depending on the shape, but somewhere around order 1 to 50, depending on the shape. So CMB is lying somewhere here, and our non-Gaussianity must be smaller than that. But the future projections for large-scale structure surveys and 21-centimeter surveys are actually, they have more sensitivity. They can probe smaller values of FNL. And we see that, we see that in a lot of the parameter space, the non-Gaussianity can be actually within these future experiments. So that's good news. So the takeaway is that the chemical potential allows us the observable mass reach for the cosmological collider to be up to 60 Hubble, much larger than the kind of vanilla cosmological collider mechanism. Okay, so quick generalization to spin 1 fields. So the lesson learned from spin 0 case is that you need explicit breaking of the number conservation for the heavy particle, and the chemical potential should be implemented as this phase in the symmetry breaking term. So for the spin 1 case, we can directly write down the final coupling. So first of all, we need just like we needed a complex scalar field, we'll need a complex vector field, so 2 spin 1 fields. And a kind of first operator that you would think of writing for chemical potential would be just A mu D mu phi with the chemical potential phase. But this operator turns out to be trivial because by integration by parts, you can show that it's actually trivial. So the next operator at tree level is this dimension 7 operator. It's a little complicated, but and one can actually write lower dimensional operators which are quadratic in the vector field. Those are a little more difficult in terms of diagrams because you have to do loop calculations. So in order to stick to tree calculations, which are much more controlled, we decided to go with this high dimensional operator for chemical potential. Now, it turns out that the longitudinal mode of the vector field actually plays a critical role in this chemical potential, and it grows with energy. So to have perturbative control, we actually need the coupling to be much smaller. So it has to be smaller than whatever cutoff scale we are aiming for, like which is at least lambda. Um, and if this coupling between the inflaton and vector field is small enough, we can maintain this hierarchy that's needed for the whole mechanism to work, where mass is bigger than Hubble, chemical potential bigger than mass, and the cutoff scale is bigger than all of them. So the rest of the story kind of follows. One has to deal with spin 1 fields, but the kind of outline that I did for spin 0 kind of follows through. So let us directly look at the non-Gaussianity that you expect for spin 1 case. Again, I have the mass as a function of and non-Gaussianity. Non-Gaussianity is a function of mass for different values of chemical potential. And we see that, again, we have potentially very large non-Gaussianity if I maximize the coupling based on constraints. And it seems like it's cut off here sharply, but that's mostly because the method that we are using doesn't work very well when the mass is very close to lambda. So we've made a conservative choice to just cut it off before you reach all the way to lambda. And again, to compare with the experiments, the CMB limit lies somewhere here. So of course, this part is excluded, and you would have to reduce the coupling between the inflaton and the vector field to be within CMB bounds. But it just tells you that the signal the best signal is much larger. So you have a lot of play with how strong you have to make the coupling between inflaton and the vector to be for the signal to be observable. And again, the LSS 21 centimeter, we see that for a large range of masses, the signal can be within the reach of future experiments. So what can we do with this chemical potential? So of course, one use case is, can we look for guts? So typical gut scale is actually at 10 to the 15 or 10 to the 16 GeV to avoid proton decay. Well, the inflationary scale is large, but it's only at 10 to the 13. So there is like a few orders of magnitude difference. So with the minimal cosmological collider, it's kind of hard to reach these scales. However, if you consider orbifold guts, the scale can be a bit lower. Unification scale can be lower at around 10 to the 14 GeV. And this was kind of explored in this paper by Raman and student Shobik. But there are some issues with these minimal gut models where unification is typically not very precise, or you have to address the gauge hierarchy problem where electroweak scale is much smaller than the unification scale. And these issues are better addressed by orbifold SUSY guts, where the orbifold kind of takes care of the proton decay problem, and SUSY kind of takes care of these issues. So these models are very nice, but then the kind of cost is that the scale again is bumped to 10 to the 16 GeV, while the KK scale is lower, but it's still 10 to the 15 GeV. But now notice that with chemical potential, our range of masses that we can probe has been expanded, and it has gone all the way to 60 Hubble, which can be as big as 10 to the 15 GeV. So with chemical potential, we can actually target these KK states of these orbifold gut models. Now, in the next two slides, I will quickly tell you how the spin 1 coupling can be implemented in these guts. I will not actually show the full SUSY model building. We haven't done it because it will require a more detailed study. But SUSY is sort of to guide the target energy scale for the guts, which is 10 to the 15 GeV. But the rest of it should go through. So in the rest, I'll only focus on kind of orbifold guts and not show you the exact SUSY model. So in our case, remember, we have this coupling where inflaton is just a real scalar field, and hence naturally a standard model singlet. So we need, for this coupling to be realized, we also need this vector field to be standard model singlet vector, and we need two of them to make a complex field. So we need a gut model where you have at least two standard model singlet vectors. It turns out that the classic SU5 SO10 group does not have enough number of singlet vectors. So, but another scenario, another class of models, which is trinification, does have up to like 5 singlet vectors, one of which will be a hypercharge. So it still leaves two real standard model vectors and hence two complex vector candidates, which we can target with cosmological collider. So let me quickly show how the orbifolding is done in this model. So you have a fifth dimension where on the x5 is equal x5 of 0 boundary, you have inflaton and the gut is broken down to standard model. In the bulk and on the other boundary, the gut group is intact. And so this can be achieved by imposing boundary conditions on the vector fields such that there is basically the derivative of the standard model gauge vector bosons is 0 on this boundary, while for the broken generators, the mu itself is 0. And in the other boundary, it's again is the Neumann condition where the derivatives are 0. And this boundary condition ensures that the standard model vector bosons have a 0 mode, non-trivial 0 mode, while the broken generators only have a massive, the first non-trivial mode is the massive mode, which goes kind of 1/4 of the sine cycle. And then, so on this boundary, where the standard model inflaton lies, we have the derivative. So the A is 0, but the derivative of these gauge fields is not 0. So we can actually couple on this boundary. We can have a localized coupling where the inflaton is directly coupled to the D5 mu term of the guts gut gauge bosons. And so this is exactly the chemical potential coupling that one would need. Also notice that because we are taking the first KK modes of either of these two standard model singlet boson vectors, they have to have the same mass. So it naturally ensures that you have an almost U1 vector, complex vector. And this is kind of the only way the U1 symmetry is broken. So this kind of tells us how the gut model, in the gut model, one can realize this chemical potential coupling. From like the analysis of this paper, the compactification scale for this gut SUSY kind of orbifold gut model to work is at 10 to the 2 times 10 to the 15 GeV, and the first KK mode is then at 10 to the 15 GeV, which means that if there is high scale inflation, then the first KK excitation is within reach if the chemical potential is bigger than 20 Hubble. So with the chemical potential, can totally target at least the first few KK excitations of these orbifold guts. So I think that's it. So let me quickly summarize. I hope I've shown you how the cosmological collider physics is a direct detection of heavy fields. And the mechanism of chemical potential essentially harnesses kinetic energy of the inflaton to boost particle production beyond Hubble. The range of observable masses can be extended all the way to 60 Hubble, which in high-scale inflation can be as big as 10 to the 15 GeV. And this can be used to target guts, which are very hard to do with terrestrial colliders. Another interesting thing is the calculations at tree level, and it makes it very tractable because most of the calculations in curved spacetimes are very difficult and run into various issues. And And the kind of some future work would be to kind of incorporate inflation and the chemical potential, all of this into a proper SUSY model. Also, we are looking into finding a suitable chemical potential for SU5, SU and SO10 gauge groups. And as well as because we have in the orbifold guts, we have a tower of KK excitations, it would be also interesting to see what is the effect of multiple KK excitations on, and does it change the cosmological ladder signal, and what way can we detect that? So with that, I thank you for your attention and the invitation to speak at the seminar series, and I'm happy to take questions.